Okay, thank you. So this is joint work with Wouter, Koolen, and Malek. I'm going to talk about online isotonic regression, which is an extension of like a classical isotonic regression problem to the adversarial setting. So let me define the problem first. So suppose we are given a set of points on the real line, here x1 to x8, and in each trial, first the adversary chooses one of the points, and then the learner needs to predict a label, which is like a real valued label between 0 and 1, and the true label is revealed, and the learner suffers the squared error loss. And then, again, the adversary chooses any other point, the label predicts, the true label is revealed, and we suffer the loss again, and the game continues. And at the end, the learner is evaluated by means of the total squared loss and is compared against the best function, monotonic function in hindsight, so the best function with monotonic labeling. So we'll call this function isotonic because it preserves order with respect to the x values. So here's the protocol again. So initially, we get a set of ordered points x1 to xt, and at trials t1 to capital T, the adversary chooses yet unlabeled point xit. This it is the index of the point chosen by the adversary. Then the learner predicts, adversary reveals the label. Both prediction and the label are in 0 and 1, and the learner suffers squared loss. And the regret is the total loss of the learner minus the loss of the best isotonic function in hindsight on this data. And two things to mention here. So first of all, the learner needs to know x values, the x points in advance, because we can show that if this is not the case, then the adversary can choose x during the game in such a way that any algorithm will suffer loss, regret, which is linear in t. And the other thing is that actually only the order of x matters, since we are competing with isotonic function. It doesn't really matter that much what particular values those x have. Okay, so the offline problem is this classical problem in statistics, which is called isotonic regression problem, and this is basically about fitting monotonic or isotonic function to the data. And at least when the order is like a full order, it can be solved very quickly in linear time within T using the so-called pool adjacent violator algorithm. Okay, so since we are in online setting, let's try to use some of the online, like off-the-shelf online algorithms. We have T parameters, and we can basically look at the bounds of some of the algorithms, like online gradient descent, maybe exponentiated gradient, follow the leader or follow the regularized leader, or exponential weights, and see what kind of bounds do we have. And those bounds, of course, depends on the norm of the gradient, which denote G, and like the diameter of the parameter space, taken with the appropriate norm. But if we translate these bounds into what they mean in our problem, we see that most of the bounds are actually meaningless. The only one is the bound for exponentiated gradient, which gives us square root of t regret, but still we will show it's not optimal. And actually, we can show, at least for a standard, let's say, parameterization of these algorithms, that these bounds are up to a logarithmic factor tight. So this is really how these algorithms behave. Okay, so since our algorithm, which we'll use, will be a modification of the exponential weights algorithm, I will show the first why the exponential algorithm, well, when we take a uniform prior over the monotonic functions, it doesn't work. So the exponential weights algorithm is defined in the following way. So we take a prior over all monotonic or intertonic function, then we update it to the posterior, which is a prior times e to the minus half total loss. The half is this concavity constant, and then we predict with the posterior mean. And if we take a simple example, when we have 100 x points on the 100 x points, and the adversary will only choose labels equal to 1 all the time. So initially, the prior mean is like a linear function, and then when we get more data, the posterior should concentrate on 1, but it's actually moving very slowly. And even at the end of the game, the posterior didn't really change that much comparing to the prior. And the main reason for that is that uniform prior puts a lot of mass along this diagonal. Actually, exponentially more mass comparing to the boundaries. So our modification is very simple. We basically choose a different prior. We choose a so-called covering net, which is the set of functions which take out only k plus 1 values at each point. We take these values distributed uniformly, and we call it a covering net because any isotonic function is close to one of these functions from this set fk. This can be efficiently implemented by dynamic programming in O of k times t trials time, and even we can get speed up if the adversary reveals the label in isotonic order, which we actually in general do not assume. So we have a regret bound for this algorithm. So given that k is chosen to be roughly of order t to the 1/3, we get a bound which is also of order t to 1/3, and this is essentially optimal because there is a matching lower bound up to a log factor. And the proof idea is very simple. So we decompose the regret into difference between the loss of the algorithm and the best in this covering net plus the loss of the best in the covering net minus loss of the best overall. And the first one can be actually bounded using standard exponential weights analysis by the log of the size of the of the class. And the second one can be bounded by t over k squared. And this is like a very specific bound for this problem. It wouldn't hold in general. It uses properties of isotonic regression function, so-called averaging properties of isotonic regression function. Okay, so here is how our algorithm works on this problem. So we see that contrary to the previous case with uniform prior, the posterior actually concentrates quite quickly around value 1. Okay, so we also have some more results, like for the noise-free case. So in noise-free case, we assume labels are isotonic, which means they are actually revealed. The revealed labels are monotonically increasing, which means that the loss of the best isotonic function is 0. And then we can actually determine exactly the min-max regret equal to it's logarithmic, and this expression is exact anytime t plus 1 is 2 to the some integer. And even if we simplify this problem even more, if the labels are not only noise free but they are also revealed in the isotonic order, then the problem becomes really simple and the min-max regret is bounded above by 1. And we also considered other loss functions. One was the entropic loss, which is like the expected log loss when we treat the label as the parameter of the Bernoulli distribution. And we get the same bound in this case. And the only difference is that this covering net that we use, it needs to be obtained by non-uniform discretization. So you need to choose points more densely closer to the boundary. And we also consider absolute loss. But in this case, it seems like the exponential gradient algorithm achieves essentially the optimal bound square root of t log t, and we have a matching lower bound omega of t, of square root of t. So just to summarize, we think this is interesting because it's a practical problem on which most of the standard approaches fail. We gave efficient algorithm with optimal regret. I would like also to mention related work. So there are two papers in the general online non-parametric regression framework. One is by Rackling and Sridharan, and it talks about like min-max regret in general on a non-parametric regression, and actually using their theory we could get the right min-max regret, but this is non-constructive, so we don't get the algorithm. The second paper gives the algorithm, but it's more complicated. It's like a two-step algorithm, exponential weight on the top of the exponential gradient algorithm, and it's not clear whether it would be implemented, efficiently implementable in our setting. And we have two open problems. So first of all, we are not really happy with discretization of the prior. We would like to have some kind of a continuous version of the prior which would work. And second thing is obviously to extend it to the partial order case. Okay, that's it. Thank you very much.